So now, if you looked in any one of these high-density smartphones, we'd find a lot of 3D packaging. We would see some of these stacked memory parts like I showed you earlier. There would be some cases where, as I mentioned, you'd have a flip chip on the bottom and then wire bond on the stack on the top. Or you might have these package-on-packages that I mentioned here. In this case, you can see that there's multiple memory die in the top package, a logic die on the bottom, and that's in the digital baseband section. So if you look at this, you'll see a lot of these different 3D packages inside your smartphone today. So if anybody wants to bring up their smartphone after we finish here, we'll take it apart and look at them all. So then now we want to talk a little bit about this new technology, which was the reason I was invited to come here to begin with. But before we could talk about the new stuff, first we had to get a little background on all the old stuff. So the new hot thing everybody wants to talk about is 3D IC. So it's basically taking die and stacking them together to give you the most thin possible structure. So this is the idea of what we're going to do. We're going to take a die, and we're going to have these things called through silicon vias through it. And then each of those die, we're going to stack on top of each other with this, connecting them with this bump. Now, typically, we're going to use a process, a reactive ion etch process. You could use a laser, but most people are using what they're familiar with in the fab side. And then you're going to fill it with, people have done a lot of things, but mostly people are filling it with copper. And this via is like 5 to 30 microns, but that's going to be, we're going to put a bump on this thing, and we're going to connect these chips together once we finish this. And oh, by the way, we're going to thin this down to about 50 microns, which remember, have you ever seen a 50 micron thinned wafer? It looks like a potato chip because it wants to curl up. So handling this, that one would have really broken in my luggage. But anyway, and then, basically there's a whole process to go about doing this, but that's the idea of what we're doing here. So everyone wants to have one of these things with a TSV. This happens to be a picture of some of the early work done at Intel. The reason we want to do this, go to this trouble, is because this whole solution where we put the chips that close together solves our interconnect delay problems. It solves our bandwidth bottleneck. It solves the problem of device latency. It solves a lot of the power management issues because when we put things together, they'll have a lower power, and you'll see some of that when we go through some of the charts. But there are a lot of issues before we can go and do this in high volume manufacturing. Issues including EDA tool availability, a manufacturing process that has very high yield, especially when you talk about thinning this. We'll talk a little bit more about how we're going to thin this structure and bond it together. The thermal part, gee, I'm stacking logic and memory. My memory has an operating temperature of which it can't exceed. If I put a logic device on it and it's hot, what happens to my memory? It gets hot. So we have to have a thermal solution. Test and reliability issues, we have to have business infrastructure. And we have to compare the cost of this to all those other alternatives that I showed you out there. So everybody has a roadmap that looks like this. And if you look, they'll have things like a package-on-package, maybe a system-in-package where you just have a couple of die sitting next to each other. But the ultimate package in terms of the height of the package and the form factor would be this TSV-type package. Now, it's an ultra-thin, ultra-compact package. So if you were just stacking die on top of each other with little bumps to connect them, that obviously is the best solution from a PowerPoint slide. But getting this thing into production is really tricky, and that's what we're going to talk a little bit more about. And that's why these timelines keep shifting out every year. Everybody has a different roadmap with a new shift out because they've found something else they could do. This is a demonstrator device that Samsung put together a long time ago. And I used to say if I had $1 for every time somebody showed this slide, I'd be retired on a beach somewhere. So one of the conferences, somebody came up and gave me $1. Anyway, so why do we want to do this stacking if you're thinking about the mobile phone space? We got that phone. What's the matter with my phone? It gets hot sometimes. The battery doesn't last long enough. But if you were to go to something we call a wide I/O, where you stack the memory and the logic together and connect with those little bumps and the through silicon vias that I showed you, we would have a lot thinner, smaller form factor product. It would solve our problem with the memory bandwidth and improve the memory power efficiency, which is what we really want. And basically, that's really what we're looking for, and why people like Qualcomm, people like Samsung are working very, very hard to make this kind of stuff happen. So we really have performance and form factor drivers to get this technology moved into production. But it's not easy. So this gives you a little bit better idea in a graph about explaining that wide I/O is going to offer us twice the bandwidth of a low-power DDR2 memory at the same power. Twice the bandwidth at the same power. Now that's very powerful. And that's what's really driving people today to get this technology into high-volume manufacturing. And it will happen. It just takes time to do that. So we've seen a lot of, also we've seen a lot of introduction of stacked DRAM with through-silicon vias in terms of samples and things like that. We've had a lot of programs announced by Elpida, Hynix, Micron, Nanya, Samsung. Tezeron over here is the only people that have been able to deliver some of these memory in production today for some specific government programs. But Nanya's still there. They actually put a press release the other day and said they joined up with Micron in this cube thing that Intel and IBM have also joined up with. So we've got a lot of people working on trying to stack some memory. This cube concept has actually a controller in there as well. So as soon as we figure out how to stack that, that is something that should go to production fairly soon. These are some of the early stacking that Elpida showed. Elpida is pretty much expected to be acquired by Micron, and then maybe some of this technology will get commercialized. But the idea is to stack a DRAM together so that you'll have a very, very high performance solution. And the people that really want this solution are people in the server business, because they really want a lot of this memory stacked together. So we have a lot of people trying to drive that to happen, but it's always a little bit more challenging. And here's some of the challenges. First of all, we've got to design this thing. So we have to have EDA tools so that we can use. We need some thermally aware tools. If we're going to stack memory, we don't have to worry about the thermal issues, right? Because we're not really heating up those with each other. But we do if we put a logic and a memory together. So there's a bunch of bright people around Stanford working on some possibilities for thermally aware design tools. So if those guys could get funding right away to do this, because there's a lot of interest in that. Floor planning tools, routing, power signal integrity, a lot of work could be done in this area. But those things will happen. We've got to put those little bumps on there to connect these things and do assembly with them. And those bumps can be like 40 micron pitch, really tiny pitch. So you've got to have a very precise bonder to put those two chips together. Well, guess what? If it's a precise bonder and there's really little area and you got to put them together, that takes a lot of time, which means throughput goes down. And that bonder is very expensive. So those are kind of things that we wish we could have a better solution for. Wafer thinning. This is actually the biggest problem we have right now, and you'll see why when we talk about this a little bit more. The idea of those wafers being stacked together, we're going to thin them down, we're going to process them some more, and then we're going to stack them together. You have to have very high yields, because remember, anything in the whole step that's with a yield of 0 would make the whole thing 0. We want to work on some better thermal solutions. We want to work on some test issues and infrastructure. Who's going to do all this stuff? What's our supplier chain look like? And then how does this cost compare to other things? Thermal management. This is actually basically, I think we're kind of beating this to death. Everybody knows that we need some good thermal solutions, because these chips in the stack might overheat if cooling's not provided. The space might be too small for some of the cooling channels. It's a very, very small gap that's in here, so you'd need a larger maybe gap for fluid flow. The thinning of the chips actually creates very extreme conditions for some on-chip hotspots. So some people have proposed that copper vias might help. This is before the thermal vias. You can see how hot that is. This is after thermal vias. So we might have some help by the fact that we're using copper vias in this thing. But we still have a lot of work to do in this area, and a lot of companies are working on this. I think the problem will be eventually solved. Now this is a real problem in it. Okay, this is where we're going to stack these wafers. So what's going to happen is we've got a silicon wafer that's going to come in. It's going to be trimmed around the edges. It's going to be clean. We're going to have a silicon carrier wafer, or this could be a glass wafer. And we're going to temporarily glue that wafer that just came into this carrier. So that's called the bonding, wafer to carrier bonding step. All right, then we're going to thin it by grinding it with a traditional pot process. Okay, so this is going to grind down to say, ooh, 50 microns or less. Okay, so this is we're going to have some, wet, dry CMP kind of processing going on and some cleaning once we do that. That's not a problem. Then we're going to basically backside process this thing with some bumps or things like that so we can connect it to the next level. And then we're going to peel that structure off that carrier, and then we're going to put it on a dicing tape and do some other things and do some more processing to it and stack it. Now, think about this. It's a very thin wafer. It's 50 microns or less. So when you start trying to peel this thing off the carrier, a lot of times it breaks. So this is a materials science problem. It's a mechanical engineering problem. It's every engineering problem you can think of in one particular process step. And guess what? The yields in a lot of this, for a lot of people, have been 0. That means that's why a lot of people haven't been shipping this stuff yet. So we need some better way to do this thinning. Remember the Tezeron part that I showed you a little earlier, and I said that those guys were actually one of the few people that are shipping stacked memory? That's because in their process, they bond this together, then they grind it back, but they don't ever peel it apart before they start putting it together. So we could use a lot more work in this area because this is kind of a showstopper. But the industry's making progress. We have a lot of new materials that are being introduced and some new equipment that's being introduced. So we'll have some results, hopefully, in the next year that'll help us. Test issues. How do you test those things? Remember the problem I talked about earlier. When we first went to stacking the die, we said the best solution was if you just wire bonded that logic and memory in a single package. It was a really thin, good performing product, but we had these issues with test. So we still haven't figured out these issues with test today. One of the ways that we could do this is Intel says we could have a good enough die so that we could have built-in self-test. In memory, every paper you'll see from Samsung at IEDM will talk about redundancy. Oh, I'm sorry. KGD means known good die. Known good die. That's why it could be a good enough or probably good die. That might be good enough. But so you have to do, you would like to be stacking good things together. Because if you stacked a whole bunch of stuff together and it doesn't work, then you have to throw the whole thing away. So part of this problem is we've got to have a test strategy for this. We've got to have a test methodology. We've got a lot of design for test that has to take place. And we probably need some probe cards for the memory. Although we've had a lot of people talking about using the built-in redundancy, built-in self-test, a lot of things like that. And we have some people that can make their own probe cards. A lot of other people are going to have to buy them. Non-contact testing, there's a lot of research work that's been done in Japan. So mechanisms that allow us to touch this, not touch the wafer, but still guarantee that it's good. Maybe inductive capacitance, optical tests, some kind of optical measurements or something would help us in this area. So we really have a lot more work to do in the test area, and probably we'll see a lot of papers coming up in the next year or so dealing with that. So, okay, so now if we figure out how to do all that stuff, then we've got to figure out, well, who's going to put this stuff together? Is it going to be the traditional back-end processors like Amkor, which are called outsourced assembly and test companies? Amkor, OSAT is the term that people use. Those are like Amkor, ASE, SPIL, Stats Chip Pack. Basically, they're people who say TSMC is a major foundry. Okay, a lot of people have their designs fabbed at TSMC. And if TSMC does it, they would like to do all the assembly for it. But they don't have a lot of expertise in this area, so there's questions about whether they should do it all, whether the subcontractor should help them. And everybody wants to have a second source. So right now we have a lot of confusion between who's going to do what and how these technologies are going to be handled, what's the supply chain, and what if it comes a memory from one company and a logic from the other, who's going to do the bump assembly and test, who's going to do the thinning, who's going to do the singulation. So we're still discussing all that. So while all those issues are going on, we got to figure out what alternatives we could do. So one of the alternatives to a full 3D IC is what if we just took part of that stuff and we put it on a silicon interposer, and we had the die communicate with each other through the interposer, so they're not stacked on top of each other, but they're really pretty close together. So if we did that, we could call that a 2.5D solution, and we could have interposers in with the through silicon via in it. So there's some advantages in this. You could also use the silicon to handle the stress for the large die with the ultra-low K dielectrics. We could incorporate some integrated passives in there too. That would be kind of nice, like capacitors. We could also, this would be maybe an interim solution before we got to do the full-blown 3D IC. And this is basically a planar kind of module. So we could also do other things like just continue using wire bond die stacks, or we could continue using package on package. But let's look at a couple of those interposers. Here's an example of, there's all types of interposers. These are foundry people making interposers. Basically, these are people with lines that are going to produce interposers. Interposers being the silicon carrier, basically. There are people that make MEMS devices that also could make interposer. And there are people that do some integrated passive devices in silicon that could do these. So this is what an interposer looks like. This is the interposer right here. And this is the package substrate. This is a laminate substrate. And this is the die. And this FPGA is partitioned into 4 die, as I'm going to show you. And these are mounted on the silicon interposer or carrier, and then they're attached to the laminate substrate. So people that are doing this, Xilinx is already shipping this part. Altera's announced something with it. There's a lot of ASIC designs by many companies, and a lot of people in the graphics space looking at it, and possibly maybe some, tablet people would look at it. This is what the basic idea is. This is Xilinx, what they call a stacked silicon interconnect. So here's this idea of this interposer. Now, this die, this FPGA, has now been a partition design so that we've divided the die, instead of this one big hunkin' die where we have to send the signal across it, we've partitioned this into 4 slices. These slices are fabricated at 28 nanometer node technology. And then you can bend these, and so basically select the good ones. They're bumped. And then we're going to put them on this interposer that has the through silicon vias and redistribution layers, so that these chips are going to communicate right here. Side by side, they're going to communicate through this interposer to each other. So they're going to act as a function of like one big die. And then this silicon interposer is going to be placed on this package substrate. And there's vias connecting here. So this is now a ball grid array package. Remember, we started out with a ball grid array package structure. But it's multiple die in not a 3D package, a true 3D, where they're stacked on top of each other, but it's still a 3-dimensional structure. But it actually functions as if it were a single device. So these things, here are the micro bumps, as I mentioned, where you're accessing power and ground, logic regions, and basically you can see the little bumps right there. And then these are, you can see that these are connected. That's how the die are communicating with each other. This is basically the through silicon vias are here. They're basically only bridge the power and the ground IOs to the C4 bumps on the bottom. And so there's a very coarse pitch on the bottom, so you're not, this is a very fine pitch, a micro bump. This is a coarse pitch. So this is not as expensive. And then the substrate doesn't have to be as expensive either. So basically, you're then, this passive interposer process is basically an older technology. So it's 65 nanometer generation node technology, basically with 4 metal layers on it or redistribution layers on it. And then basically, it's a lot less expensive to fab something at that level. Okay, so this is actually what's been in production today. And because these are side by side, we could just put a heat sink on the top and not have to worry about basically a lot of power sitting on top of each other as if they were stacked die. So this is actually a product that was introduced and is shipping in production. And one of the big things about this is with this structure, you're able to achieve a greater capacity with this structure, with the die side by side, you're able to achieve 4x the bandwidth if you just had a single die solution. And this is even better, a fourth of the power to get this type of performance. So it's a lower power solution by doing this partition design than it would be if you put 4 die in a single package. So this is very, very powerful type technology. Here's the other way we could do this interposer. We could say take stuff that's an FPGA, we could put some other devices on it, in this case some 28 qubit transceivers, and then these could communicate here across the silicon interposer just like the same partition die did. So a lot of different devices could be put on this interposer, and in the old days we used to call these multi-chip modules, but now we're calling them something fancier, 2.5D. But suffice it to say that Xilinx took a really long time in putting this stuff together, even getting this interposer solution together. They started this development back in 2006, and they're just now shipping this technology. In other words, to do a new technology like this, to do something different, and this is just the easy thing, the 2.5D solution. It takes a lot of time, a lot of activity. They did a lot of acquisitions of software companies, a lot of test vehicles, so it's a long process. So it basically has been now a successful technology. So, you know, so everybody's trying to do some way to achieve some of the same performance advantages using this interposer type structure as opposed to going to the full die-to-die stacking on top of each other. This is another introduction that is actually a real product. IBM has worked with a company called Semtech in Southern California to develop an interposer that connects basically analog functions with some silicon germanium technology that they fab for them. And basically this is on an interposer, and the applications are things like fiber optic telecom, high performance RF or test equipment, or radar systems, things like that. And so this technology is in production today as well from IBM. So I wanted to conclude by saying that there's a lot of real engineering work for 3D ICs, a lot of structures that have been fabricated in prototypes, and a lot of processes that are still needed to be worked on for us to get the yield up to really see that technology go into large-scale production. There's a lot of applications that are using through silicon vias. Image sensors and MEMS, where they have backside vias, these have been in production for quite some time. There's a lot of research going on in wireless applications, high-speed logic. A lot of the substrates, the silicon substrates, are using the technology. And we have a lot of future memory applications that we think will use this technology depending on the cost trade-off and reliability data. And oh, by the way, does anybody ever drop your phone? Do you want your phone to work after you drop it? So whatever this new technology is, has to pass a drop test. So regardless of which technology we're talking about. And cost performance ratios, did you want to pay $1,000 for that phone, or did you want to pay $300? Well, so this also makes a difference in the adoption in each application. By the way, if you wanted one of those Xilinx parts, they're about $15,000 or $20,000 for the part. So, you know, they can afford a silicon substrate. They can afford to go to a full 3D process if they could yield it. But the cost performance in each application is different. So you have to look at it application space by application phase. So we're going to see silicon interposer adoption underway today. There's a little bit of still issues on who's going to supply the substrate, who's going to do the assembly of this thing. Is it going to be all done at TSMC? Is it all going to be done at subcontractors? And we'll still see a lot of things like those package-on-package, wire bond stacks, and combinations of wire bond flip chip stacks being used in production for probably a long time in a lot of your products. Okay, so that's all I have for you today, and I'll be happy to entertain questions and have you come up and look at some of these sample parts that I brought so you can actually see what these things are, other than that laminate substrate.